All right, AP Chem, let's talk colligative properties. So this is kind of the last big concept we have to talk about in AP Chem. I'm going to introduce you kind of to the colligative properties and what they are and kind of how they operate. And then when we're back together live, we can talk through some of these practice problems. So again, for all of these colligative properties, all of them come with an equation, but more important than being able to calculate, to be able to plug in variables and chug out an answer, more important than that is being able to describe the relationship of the variables in these different equations. So you want to be able to say, if X goes up, what happens to Y? If Y goes down, what happens to X, kind of a deal. So like a general relationship. Now your book is going to walk you through some of these calculations, because by doing the calculations and kind of observing the changes that go with that, you're going to have a much better idea of how these equations work. But they're all really plug and chug equations, and the relationship is what's important. Okay, so let's start talking through them. Colligative properties in general, it's a property of a solution, obviously, because we're in the chapter about solutions again. So it's a property of the solution that's dependent on how much is present, not necessarily what is present. So you can see the little definition here talks about how it's dependent on quantity, but not kind. And that's exactly true. It really doesn't matter if it's an ionic compound or a hydrate or a covalent compound that's present. It really doesn't matter what's present. It doesn't matter if it's a solid or if it's a liquid mixed with a liquid or if it's a gas that's been dissolved. It doesn't matter what kind of thing is present. What matters is how much. And that is good news for us as chemists, because we love moles. And moles is a perfect description of the quantity. Moles is a counted number, right? It's an amount that's present. It's not necessarily swayed by how much each piece weighs or how much volume each piece takes up. It just tells you how much is there, right? And so all of these properties are dependent on how much is there, and it's not really as important what is there. So there's 4 basic colligative properties we're going to talk about: freezing point, boiling point, vapor pressure, and osmotic pressure. So as we go through all of these, we're going to give it a short definition, talk about the factors involved, and then look at an equation. All right, so vapor pressure. Really, is this the first one Yep, I guess it is. Okay, so let's talk about vapor pressure. It's probably the trickiest concept to wrap your brain around. So let me kind of step you through what vapor pressure is. So we have been talking the last couple of days about pressure, right? Pressure is a force that's exerted over a specific area. In terms of gas exerting a pressure, that force is translated into little molecules, little gas molecules that are bouncing off of this. So you can kind of get an idea of a gas pressure. Think about atmospheric pressure, for example. If we are talking about the pressure of our atmosphere, right, that exists, we are all under gas molecules. And all of these gas molecules are being pulled toward the center of Earth by what? By gravity. Gravity is pulling all of these gas molecules that are in our atmosphere down, and gravity is pulling them down on us. So if I hold out my hand here, okay, let me attempt a hand. All right, that's not too bad. Okay, so there's my hand. That's my area that the atmosphere is striking, right? So I have all these gas molecules above my hand, hitting my hand and bouncing off. And actually, all I am supporting the weight of these gas molecules being pulled toward the center of the Earth all the way up into space. So you can think of all of these gas molecules like a column of air that extends all the way up through space. And obviously down by us, the gas is going to be denser. And as we get like to the top of a mountain, it's going to be a little bit more sparse. And as we get up by like the outliers of space, the gas is super far and few and far between, right? But this whole column of gas molecules are being pulled by gravity onto my hand, and they're exerting a force on my hand, and that's what we call atmospheric pressure. Okay, so we know what pressure is as it's caused by a gas. We know what atmospheric pressure is. So now we're going to look at vapor pressure. So vapor pressure occurs inside a closed container. So this is kind of the first thing we need to have in order to talk about vapor pressure. So vapor pressure doesn't occur above my hand into the atmosphere because it's not in a closed container. We need a sealed container. And then also in that sealed container, you need a liquid. So let's talk about water. We place water in a jar and we screw on the top. Okay, now we definitely have water in that jar. We also have some atmospheric gases in that jar. So let's say we have O2, we have N2, we have CO2, we have some H2O. All of these are little molecules that exist in my jar above this water. Now, what's going to happen is these water molecules are constantly in motion, as all things, as all molecules are. They're bouncing off the container walls, they're bouncing off the surface of the water, and sometimes when water molecules hit the surface of the water, they escape. Pop! We get a little water molecule that has escaped into the atmosphere of our closed jar. Okay, so if I just put some water in this jar, I'm going to get a lot of water that starts escaping. Pop. Here's another one out in the jar. And eventually I'm going to establish so much that these molecules that are now bouncing off each other, bouncing off the walls, are eventually hitting the surface and pop, going back in to solution. So eventually I'm going to establish this equilibrium where the water molecules in the water phase are leaving the water phase, going into the gas phase at the same rate as the water molecules in the gas phase are striking the water and becoming liquid again. So we get this equal rate of water escaping into gas, water re-entering the liquid. And what do we call that when we have equal rates of two things happening? We call it equilibrium, right? So we've established an equilibrium of water escaping into the gas phase, water re-entering the liquid phase, going in both directions at the same rate. This is equilibrium. Okay, so once that equilibrium has been established, we can look at the gas phase in our jar. And the gas phase in our jar now has a set amount of these water molecules that have escaped. And that those water molecules are exerting a pressure inside that jar. And that's what we call vapor pressure. It is the pressure of the vapor. We call it vapor because anytime you're referring to a gas as vapor, that means that normally it's a liquid, but for some reason right now it's a gas. So like if we pour a cup of hexane for ourselves, and we're sitting by this cup of hexane and we start to smell the hexane, we'd say, oh, I smell the hexane vapor, right? We call it vapor because when we originally dealt with it at STP under the conditions that we're dealing with it, it was a liquid, but some of it has turned into gas the gas phase, and now I'm smelling that. So we call it a vapor. Something that would originally exist as a gas, like carbon dioxide. If you're sitting at room temperature and hanging out with some carbon dioxide, it's going to be in the gas phase. It would be unusual. You would have had to exert energy and do something specific to the carbon dioxide to force it into the solid or the liquid phase. So something that's normally at the gas phase, we would call that a gas. So we don't say, oh, I'm breathing out carbon dioxide vapor. No, we would say, I'm breathing out carbon dioxide gas. So that's the difference between a vapor and a gas. So vapor pressure is the pressure of a gas that has escaped the liquid phase, gone into the gas phase, and is now exerting a pressure inside that closed container. Emphasis on closed container. Has to be a closed container. Okay. So now we know what vapor pressure is. Here you can see a very concise definition of vapor pressure. A liquid in a closed container will establish equilibrium with its vapor. And the pressure that vapor exerts is vapor pressure. Okay, so the vapor pressure that's established, it's going to be affected by the liquid that you put in there. If you compare liquid water versus liquid mercury, liquid water is going to establish a higher vapor pressure because of the molecule that it is. Mercury has unusually high attraction for itself, and so it's going to be harder for that molecule to escape the attraction to itself and enter into the vapor phase. So the vapor pressure is affected by A, what the thing is. B, it's going to be affected by how much surface area is showing. If you have a super tall container and you have a super long container that both contain the same amount of water, okay, the one with more surface area is going to exert a higher vapor pressure because there's more surface for the little molecules to escape out of. So surface area makes a difference. Intermolecular force, which we haven't talked about, but that's what I was just saying, like water versus mercury, what the molecule is itself and its attraction to itself is going to affect how much vapor pressure is established. And then temperature, of course, is going to make a difference. If you take a glass of water on your kitchen counter, it's going to establish a vapor pressure. If you take that glass of water and you put it in the microwave, which you shouldn't do if it's closed, but if you did and somehow it didn't explode, there would be a different vapor pressure inside of that glass that you microwaved because the temperature is higher. So temperature has an effect on vapor pressure also. If you hear the term, you're going to hear these two terms, volatile and non-volatile. So a volatile solution, a volatile liquid, is a substance that's going to allow the liquid to escape into vapor fairly easily. So anything that you smell, if you uncap it and you smell it right away, it's volatile. Vinegar is fairly volatile. That liquid is going to escape into the gas phase fairly easily. And our evidence that it escapes is that we smell it. Ammonia, wholeheartedly ammonia, is going to be a volatile solution. It's actually even a volatile solid. You're going to smell it and it's going to be a super strong smell. If something is non-volatile, it's not going to escape very easily into the gaseous phase. It's going to have no measurable vapor pressure. Mercury would be a good example of that. Mercury is not going to escape very easily and establish a vapor pressure. Things that are volatile, that's why our hood exists. So if you can see across the room, this thing, where is my little, this thing, nope. This thing right there. That's called a hood. And basically there's a little switch on the side here, right there, that I can turn on. And basically what it does is it like sucks the air up and hopefully runs it through a filter before it kicks it out of like into the atmosphere. And so anything that's volatile, we put in the hood. We're going to use the hood to deal with that thing because we don't want to be breathing in chemicals. So anything volatile, we deal with in the hood. When we talk about hexane is this super weird compound. It's actually nonpolar. It's nonpolar, it's a hydrocarbon, so it's extremely flammable, and it turns into vapor very easily. It's really fun to play with, also carcinogenic, so you got to be careful if you're playing with it. But you don't want to breathe that stuff in, and so whenever we're dealing with hexane, we're going to deal with it in the hood. Stuff like that. Ammonia, same thing. Ammonia, A, it's going to give you a headache if you smell too much of it. B, it can technically make your brain bleed if you're dealing with it in strong enough quantities. You never want to be in a locked room alone with ammonia, because ammonia can actually do damage to you. It can go through your nose into your brain and make your brain bleed. So something like ammonia, we would also deal with in the hood. Maybe vinegar too. I mean, vinegar has this powerful smell. It's kind of obnoxious. It's not really dangerous. But just to avoid the smell of vinegar, we might deal with it in the hood. Okay, so here is the catch to vapor pressure. Adding a non-volatile solute always lowers the vapor pressure. Lowers being the key here. So non-volatile would be something like a solid if you mix a salt in to your water, or something like sugar. Sugar is non-volatile. It's not going to spontaneously turn into a gas, right? So things like that, or something like hexane. Oh no, hexane's very volatile. Something like mercury. If you could get mercury to like dissolve into your mixture, that's going to lower the vapor pressure. So let's look at why this occurs. So like we said, with vapor pressure, here's our liquid line. I have lots of water molecules in here, okay? So as these molecules bounce around, they're going to hit each other. They're going to hit the side. Eventually, they're going to hit the surface, and some of those water molecules are going to escape into the atmosphere. Now, whether they escape or not, just like we were talking with the relationship between mercury and water, whether mercury escapes or not depends on how attracted that water molecule is to itself, to another water molecule. So if we can increase that attraction between the two molecules, we're going to decrease the vapor pressure. Think about it as if you are trying to, run away from somebody. If that person has a grip on you, if they're holding you very tightly, it's going to be much harder to get away from them. If it's like a 2-year-old child, for example, that doesn't have a very strong grip on you, then it's going to be much easier to break that grip and escape. So anytime you add something that's a non-volatile solute, you're going to mess with those attractions. So for example, let's say we dissolve into our water some Na plus and some Cl minus. So we're going to put some salt into this water. Now, salt is non-volatile. It's not going to spontaneously turn into a gas by itself, right? And salt is also attracted to certain parts of that water. And so it's going to mess with that attraction, and it's going to keep, I guess that's the wrong part of the little molecule. Let me flip that molecule around. Okay, it's going to keep those molecules from escaping from that liquid. And so if less molecules can escape, then all of a sudden you have less molecules that are striking the side of the container, striking the surface, bouncing around, and causing that force on the surface area, which is what we call pressure. So anytime you enter in a non-volatile solute, anytime you dissolve in a non-volatile solute, what you're doing is changing the attraction so less molecules can escape, and therefore you will have less molecules in the vapor phase that are exerting a pressure. Adding a non-volatile solute always lowers the vapor pressure. Keyword here, this is the relationship you need to remember. Guess what? There's an equation. It's called Raoult's law. And it also, just like Henry's law, that was a relationship between solubility and partial pressure. This one also involves partial pressure. So Raoult's law is talking about the partial pressure exerted by the solvent vapor above a solution. So this PA is when the water molecules escape out and are in the vapor phase exerting a pressure. This PA is the pressure that they are exerting. That is the vapor pressure. Okay, now vapor pressure is dependent on what the original pressure is. So P is partial pressure. This little degree symbol is, we say naught. So we would call this a P naught. And usually naught is an indication of the initial like measurement. So before your experiment started, you would have P naught or concentration naught. Okay, so that naught symbol, that degree symbol, is an indication of the initial state of being. And then A is talking about like it's a vapor pressure again. You could say like, we could call it P naught V, so for like the original vapor pressure, but for some reason they're using A's and not V's right now. So let's just roll with the A. So P naught A is the vapor pressure of the pure solvent. So if the solvent was there by itself, this is the partial pressure that would be exerted. So if we have a cup with some water in it, if it's just water, the vapor that is established by that pure water up above, that is P naught. Okay, so basically what this relationship is saying is the pressure of the solvent is going to change when you add a solution, when you add a non-volatile solvent. And the factor by which it changes is actually the mole fraction, chi. It's the mole fraction of the solvent in the solution. So again, there is an equation here. Again, your book's going to run you through a couple calculations. But again, the most important thing that comes out of here is that relationship. So let me kind of walk you through a couple things and we can talk about the example that's down below. So if you have a mole fraction of the solvent, remember it's the moles of your solute over moles total. So moles total is going to be solvent plus solute together. So what we're dealing with here in the mole fraction is a part out of a whole, right? So basically you're going to be multiplying that pressure of the pure solvent, that P naught vapor pressure, by a fraction always less than 1, right? If you're measuring a part out of the whole, you're going to have like 90%, 0.9, or 60%, 0.6, or 30%, 0.3. It's always going to be less than 1, which means you're always going to be lowering the original vapor pressure to get to that new vapor pressure that's exerted after you add that solute in. Okay, so let's look at this example down here. We have a vapor pressure of water. It's 17.5 torr. So this is P naught of your water. So when water's by itself, it exerts a vapor pressure of 17.5 torr. And this is going to happen at 20 degrees Celsius. And the only reason they tell us that temperature is because if it changes, then we have to restart the whole discussion. right? So basically they're telling us that's the temperature through the whole discussion. It's not going to change. You don't have to worry about it. Okay, so we have an original vapor pressure of water when it's by itself. And then glucose is added. So glucose is a type of sugar. It's going to be a polar covalent molecule. It's going to be added to the water. So now we have a mole fraction. So notice the mole fraction of water is 0.8. The mole fraction of glucose is 0.2. So if we look at water over the whole, water takes up 80% of our solution. If we look at glucose over the whole, glucose takes up 20% of the whole solution. Okay, so vapor pressure of water over the solution will be what compared to vapor pressure of pure water? And if we want the partial pressure exerted by the solvent vapor, we need to use the mole fraction of our solvent. So this is the tricky part. Our solvent is water, right? So we're going to use the mole fraction of water, not of glucose, because we want partial pressure of water once the glucose has been added. We don't want partial pressure of glucose. So we're going to take P naught of water. We're going to multiply it by the mole fraction of water, and we're going to get the new vapor pressure of water. So basically, it's 80% of what it was originally. And that's 17.5 torr. So what is 80% of 17.5 torr? 14 torr. Notice that mole fraction doesn't have a unit because it's moles out of moles, right? Technically, it's moles of water over moles total, but typically we don't put a unit on here. And here's our new vapor pressure of water. Notice it's gone down. It's gone down proportional to the mole fraction. Okay, so here's another example that we can do together. Let's talk about boiling point and freezing point. Okay, so first of all, a quick definition for boiling point and freezing point. Boiling point is a temperature. So whenever I ask you, what's the boiling point of XYZ, you're always and forever going to give me a temperature. You're going to say 20 degrees, 0 degrees, -5 degrees. Boiling point is a temperature. And it's a temperature at which a phase change happens. So what phase change happens at that temperature of a boiling point? So boiling is when liquid turns into a gas, right? So it's the temperature at which a specific substance turns from a liquid into a gas. Boiling point for water in Celsius, 100 degrees Celsius, right? So the boiling point for carbon dioxide, anybody know? It's much, much lower. It's in the negatives for Celsius. So each individual thing has its own individual temperature at which it boils. If you hear this term normal, the normal boiling point, that is the boiling point at STP, not STP, at SP, at standard pressure. So when pressure equals 1 atmosphere, which is what standard pressure is, then you can, at that pressure, it will give you the normal boiling point, the normal temperature at which it turns from a liquid into a gas. Okay, at normal boiling point, the vapor pressure of the solution will be less than 1 atmosphere because the normal boiling point happens at 1 atmosphere. So if you turn it into a solution, it's going to happen at less than 1 atmosphere. And again, and so therefore, in order to get it to boil, you're going to have to push that temperature higher. So again, this comes down to a really similar concept that vapor pressure did. If we look at this solution, okay, we have our solution of water here, and all of these little waters are attracted to each other, right? And so That's why water is a liquid, because there is some attraction between these little molecules. Something like carbon dioxide has very little attraction from carbon dioxide to carbon dioxide, and that's why it's a gas, because there's not very much interaction between them or attraction between them. The technical term for that attraction between two molecules is an intermolecular force. And once we talk through bonding, we'll have a whole chapter on intermolecular force. Okay, so for now, if you look at the molecules in a liquid like water, they have an attraction for each other, which is why they're a liquid. But sometimes the motion of those particles can overcome that attraction and the water can escape out of the solution, right? And that's what going from a liquid to a gas is all about. Now, as you raise the temperature, what about the molecule changes? So this is one way the way you think as a chemist has to change a little bit. Whenever you hear the word temperature, what I want you to think of is motion. So at a lower temperature, molecules have less motion. At a higher temperature, molecules have a much greater motion. That is what temperature is. Temperature is a measurement of the motion of a molecule. And that's exactly what a thermometer is too. If we look at a thermometer, it has liquid inside it. Well, as that liquid gains energy and starts to move faster, the liquid actually moves farther away from each other. It hits each other, it bounces farther, it expands because of that increased energy, increased motion. It expands and we start to read a higher level on our thermometer. So really a thermometer, we say, what does the thermometer measure? It measures temperature. It actually measures motion of the molecules. And when molecules contain greater energy, they are going to have greater motion. And we read that, we measure that as a greater temperature. Okay, so going back to our drawing, if we have found the temperature, okay, or the level of motion where these molecules in the liquid phase can overcome the attraction to other molecules in the liquid phase and escape into the gas phase, that is boiling point. That's the very definition of boiling point. Now, when you put a solute in here, just like we did with vapor pressure, if you put a solute in here like sodium and chloride that are going to attract that water molecule, now the water molecule needs even more energy. It needs even more motion, even more temperature to break that attraction and escape into the gas phase. And so when a solute is dissolved in water, it's actually going to hold the water molecules in there until a higher temperature is reached. And that's what the colligative property of boiling point elevation is. When a solute is dissolved in your solution, a higher boiling point is then needed for the substance to turn from a liquid into a gas. So the colligative property is boiling point elevation. And of course, it comes with a formula. Now, this formula is listed as the calculation of this formula is beyond the scope of our class, but the understanding of this formula is within the scope of our class. So this one, you actually don't need to calculate at all. And I've taken away all the questions in the back of your book that ask you to calculate this. except for one. I'm asking you just to step through one so you kind of wrap your brain around it. And the reason that they kind of kicked this one out of the curriculum is because look at this term right here. It's a lowercase cursive m, and that stands for molality. And molality is not one of the concentrations that you have to understand. We did talk about it earlier. It's the moles of solute. But instead of being over liters of solution, like molarity is, it's over kilograms instead of liters, and it's not of solution, it's of solute. No, solvent, sorry. It's of solvent. So moles of solute over kilograms of solvent, that's what molarity is. So it is just a measurement of concentration, like molarity, like density, like mole fraction, like percent composition by mass, right? They're all ratios that represent what the concentration is. It's just measured in a different way. Okay, so the concentration is multiplied by K. Now again, K is a constant, but K is going to change depending on what the solvent is. And so for the specific solvent, you have to go look up K. And then when you multiply K by the concentration in terms of molality, what you get is how the boiling point will change. So let's say we're talking about water, and we take water and we put in salt, NaCl. Let's talk about table salt, right? We put in salt. So now we have these extra ions in here. We have these extra forces that are attracting our water, right? And it's making that water harder for it to escape from the liquid to the gas phase. And so more energy needs to be pumped in order to get the molecules moving even faster before that water can escape into the vapor phase. Okay, so initially the boiling point for water is 100 degrees Celsius. Well, if you take the molality of your solution, so moles of your salt over kilograms of water, you multiply it by this K factor, the molal boiling point elevation constant that you look up in a book. And it's going to give you the change in boiling point. Notice it's not going to give you a new boiling point. It's going to give you a change. And let's say that change is 2.3 degrees Celsius. So what is your new boiling point? Well, you know it's a boiling point elevation, so you have to add the two together, and you get, 100. Oh, I was right the first time. Wait for it. I can write this number. I can add 102.3 degrees Celsius. Okay, so notice this formula gives you the change in boiling point, not the new boiling point itself. You actually have to add it to the old boiling point in order to get the new boiling point. Okay, now this is a colligative property, just like vapor pressure. This is a colligative property, and so it's dependent on how much is present. So if you dissolve something like NaCl in there, then you have to take into account that one molecule of NaCl becomes two ions, Na plus Cl minus. So one molecule becomes two ions. So what's in solution affecting the boiling point? Not one molecule. What's there affecting the boiling point is two ions. And so what you have to do is you either have to, when you're calculating this moles of solute, you either have to use the moles of the ions, or you use the moles of your compound, and then you use I, which is probably the easier way to do it. So I is called the Van't Hoff factor, and what I is the actual number of particles or formula units that are there. So I for sodium chloride is 2, because for every one compound, it splits into two ions. So what's actually in solution? Two ions. Okay, So take a minute and think, what would the I be? What would the Van Hoff factor be for these other two compounds? What would it be for K2SO4, potassium sulfate? What would it be for C6H12O6, which is glucose? Okay, so the Van Hoff factor, remember, it tells you how many particles are actually there. So if you take potassium sulfate and you dissolve it in water, you actually get 3 ions, K+, K+, sulfate. If you take glucose and dissolve it in water, how many ions do you get? None. It's a covalent compound. So the Van Hoff factor for glucose and all organic compounds is going to be 1. So you have to be especially careful of sugars because they have a Van Hoff factor of 1. None of them are going to break into ions. You also have to be careful of like alcohols. Alcohols, organic compounds that don't break up into ions, are going to have a Van Hoff factor of 1. Ionic compounds, soluble ionic compounds, will just be the number of ions that are in. Now, there are a couple tricky ones like sodium acetate, for example, or acetic acid. Remember, acetic acid is a weak acid. So HC2H3O2. If it didn't break up at all, it'd be a 1. If it broke up completely, it'd be a 2. We know it breaks up slightly, and so the Van Hoff factor for this is somewhere in the middle. It's like 1.1 or 1.2. So there are a couple tricky ones, but usually you're not going to deal with the tricky ones on the test. Just be aware that things that are slightly soluble or weak acids and bases are only going to break up partially. Okay, freezing point depression is a very similar thing. So freezing point, again, is going to be a temperature. Okay, it's the point at which something freezes. So again, what's the phase change that goes along with this? It's liquid to solid. So it's the temperature at which something turns from a liquid to a solid. Now, when something freezes, what's happening is these molecules that are present that have some interaction, some attraction to each other. Think about water molecules slipping past each other. Well, they slow down enough for that attraction between them to actually lock them in place. And so it forms this crystallized structure. This is not what water actually looks like, but we can pretend for now. It forms this crystal structure because the molecules have slowed down enough for that attraction between the molecules, that intermolecular force, to lock them into place. So pure crystals, in order to lock into place, they need to have that molecule to molecule attraction. If you have a solute in there, again, like a salt, maybe like magnesium chloride, let's put a magnesium ion in here. If you have that ion in there, it's going to disrupt this crystal forming process. It's going to get in the way of that molecule to molecule attraction, that intermolecular force between the two water molecules or whatever your solvent is. And so what has to happen is your molecules have to slow down even more, which is going to be a low temperature, has to slow down even more so that that attraction can lock these two things into place. So the solute interrupts that crystal forming and it prevents freezing from occurring. It prevents that solid from forming. That solid won't actually form at the freezing point. You have to remove additional energy. It has to be even lower at a lower temperature for those solutes to lock into place with each other. So boiling point gets elevated, freezing point gets depressed. A good example would be calcium chloride. In a lot of places, not Oregon. You may sense some bitterness in my voice. I grew up in Michigan. And when it snows in Michigan, they salt the roads and you can still drive on the roads because calcium chloride dissolves into calcium and chloride. And those solutes get in the way of the freezing process of that water. And all that ice, instead of forming ice, it actually forms slush that you then drive through. Not fantastic for your cars, but it causes the cars to rust. That salt does. But it's really great for driving. You can still drive on the road. They don't get all packed down with ice. Good question here. Follow-up question here. What's the Van Hoff factor for calcium chloride? And hopefully you said the Van Hoff factor is 3. It's going to form a calcium and 2 chloride molecules before it actually, or when it actually exists in solution. So has an extremely similar formula. Notice it has all the same components. Molality, the K, this K is going to be a different K than the K for the boiling point. So again, you would have to look it up. Again, there's going to be that Van Hoff factor in there so that you can calculate molarity off the ionic compound, because then you're going to multiply it by the number of ions it forms, and then you're going to get a change in freezing point. Again, you're not going to get the new freezing point. You're just going to get the change in the freezing point. This one you have to subtract because freezing point is depressed. Okay, there's some practice problems we can go through together in class, and then we'll kind of summarize this together before we talk about osmotic pressure, which is our last topic for colligative properties. Okay, see you guys in class.